This is electromagnetic induction. For electromagnetic induction, varying magnetic flux is required, which is represented by delta phi. And the phi is equal to BA sine theta. But this varying magnetic flux must be cut by any conductor like wire, coil, and that is called flux linkage. So second requirement of the induction is varying magnetic flux linkage, and it is represented by N times delta phi. So there are two basic requirements. Number one, there must be flux and it must be varying. And number two, that flux must be cut by any conductor, by any wire, or the number of turns of the wire. So this varying magnetic flux can be produced either by moving the magnet, oscillating the magnet, and number two, either by connecting the coil with alternating current. So these are the two methods. These are the two methods to change the flux, to vary the flux. Number one, either by moving the magnet, and number two, either by connecting the coil. And second requirement is magnetic flux must be linked with the coil. So it is called N delta phi, and its name is flux linkage. Now there is a law for the Faraday's. It is called Faraday's law of electromagnetic induction. And the definition is induced EMF is directly proportional to the rate of change of magnetic flux linkage. So induced EMF is directly proportional to rate of change of magnetic flux linkage. Now, what is rate of change of magnetic flux linkage? N delta phi, or d phi divided by dt. So N is the number of turns of the coil for the linkage, d phi is the changing flux, and dt is the rate. So rate of change of magnetic flux linkage, this is directly proportional to induced EMF. So when EMF is written like this is E, then here constant, and N d phi over dt. Now the constant is inductance. So N d phi over dt, this inductance for the A level is considered exactly 1, mean the 100%. So the EMF induced is equal to N d phi over dt, where phi is equal to be a sine theta. So this flux is changing either due to change in magnetic field, due to change in area, or due to change in direction. Okay, now there is another law which is called the Lenz law. We have done this O level. Direction of induced EMF is totally opposite to the direction of source producing it. Mean the direction of the induced EMF is opposite to the direction of the flux, direction of the magnetic field. So direction of the induced EMF is totally opposite to the direction of the source producing it. So for this, we will put here the minus sign because this is the source which is producing and this is the induced EMF. So both are in the opposite direction. Now look, this is the coil and it is connected with alternating current source. So when alternating current is supplied to it, this is north, this is south, then this becomes south, this becomes north, first this direction, then this direction. So the flux is changing, delta phi or d phi. Now this is called the primary coil. Now the coil which is used to produce the varying flux in the physics is called primary coil. So when a coil is connected with the alternating current, it provides varying magnetic field and known as primary coil. So the voltage supplied to this is alternating like this, sine wave. Now, according to Ohm's law, voltage and induced current both are directly proportional to each other, mean the graph for the induced current will be, or the graph for the current for the and voltage will be same. So this is the voltage provided to the primary coil and this is the current in the primary coil. Now, magnetic flux density B depends on the current. So the graph of the magnetic flux density will be the same because B directly proportional to I. And similarly, the flux phi, magnetic flux, is also directly proportional to B because phi is equal to B A sine theta. So B and phi. So look, these are the four graphs due to directly proportional relation. V directly proportional to I, B directly proportional to I, and phi directly proportional to B. So these four graphs are similar, or we can write they are in phase. So this is the coil P. It is connected with the alternating current. Its voltage, its current, its magnetic flux density B at any point, and the flux at any point B. All four are directly proportional to each other. They are in phase. Now, according to Faraday's law, when another coil is placed close to the first, it is connected with the load, and this load means the resistor is connected with the voltmeter. No battery in this coil circuit, but it is inducing EMF, so voltmeter is giving you the reading. Now this is called the secondary coil. So the primary coil is providing the magnetic flux. Secondary coil is cutting that flux and inducing the EMF, According to Faraday's law, EMF induced in the secondary coil will be minus N d phi over dt. Suppose we ignore this Lenz's law, negative sign. The flux is provided by the primary coil. Number of turns of the secondary coils are cutting. And due to this flux linkage, EMF is induced in the secondary coil. Next assumption, suppose number of turns of the secondary coil, just one. So we can write E induced in the secondary coil is just d phi p over dt. So induced EMF is the gradient of the flux time graph, because this phi p, d phi p over dt is the gradient of the flux and time graph. So this is the flux of the primary. This is sine wave, and the gradient of the sine wave is the cos wave. So EMF induced in the secondary coil against time will be the cos graph. This is the graph for induced EMF in the secondary coil. Now, this voltage which is induced in the secondary, and this is the voltage which is supplied to the primary. So this voltage is the source. This VP, voltage provided to the supply, is the source. And this is the induced. Look, both are at the phase difference of 90 degree, because this is sine wave and this is cos wave. So they have phase difference of 90 degree, mean pi by 2 radian. Now, number of turns of the secondary coil increasing. So what will be the effect? So the effect will be the amplitude will increase. The effect will be on the amplitude. More voltage will be induced, but the shape of the graph, the phase difference will remain same. If we consider the Lenz's law, so instead of the positive cos graph, it will be negative cos graph. So this will be the difference only. So when we will increase the number of turns of the coil, amplitude will increase. When we will consider the negative sign, it becomes the reverse graph, mean the positive to negative graph, reflection of the previous graph. Okay, so in this example, one coil is providing the varying flux and the other coil, the separate coil, inducing the EMF. This is called mutual electromagnetic induction. So this is the example of mutual electromagnetic induction, which is used in transformer. Now, the next is self-induction. Suppose this is the coil. It is connected with alternating current. And the magnetic field is around it. It constantly changing its direction, left to right, right to left, because the poles are changing. So this is the varying magnetic field around it. So delta phi, or the d phi, is produced by the coil. Now, the coil itself, this portion of the coil, which is shaded part of the coil, is cutting small portion of varying magnetic flux. So we can write this, the coil, this coil, this one, 2, 3 turns. The coil is cutting the small portion of the varying magnetic flux because this is the area of the flux, but this portion of the flux is cut by the coil itself. So when small portion of the magnetic field, magnetic flux is cut by the coil, according to Faraday's law, a small EMF is induced in the coil itself because the coil is cutting the varying magnetic field, so the EMF is induced. So this is actually the self-induction, and EMF induced will be small as compared to the provided. So this alternating voltage is 220 volt. So we are supplying 220 volt, and 20 volt is produced by this small electromagnetic induction. According to Lenz's law, when this 220 volt EMF is directed in this direction, then this 20 will be in the opposite direction. So both supplied and induced, this is the supplied, mean the source, and this is induced EMF. Both are in the opposite direction. They are cutting each other, they are canceling each other. So the resultant voltage in the coil will be 220 minus 20. Just for the example, it will be 200 volt. So this is called self-induction. When a coil is connected with the alternating voltage, it provides varying magnetic flux. Small area, small portion of the varying magnetic flux is cut by the coil itself. According to Faraday's law, a small EMF is induced in it. According to Lenz's law, that is totally opposite to the source. So for example, this 220 volt voltage is a supplied, is a source, and the EMF induced small is 20. Both are opposite. So resultant is 200. So this is the self-induction. So self-induction of the coil reduces the resultant voltage. So self-induction causes reduction in the resultant voltage. So all motors which operate on the alternating current, right, will reduce their efficiency due to the self-induction of the coil. So in all alternating current motors, one of the factor reducing their efficiency is self-induction of their coil. So this self-induction is not the advantage, this is a disadvantage, but with the shape of the coil, we can reduce it, but it cannot be eliminated completely. So all coils which operate, which are connected with the alternating voltage, alternating current, they will self-induce EMF, and this is the disadvantages for motors. Now, third type of induction, which is called eddy current induction. Suppose we have two magnets. their opposite poles are facing, so the magnetic field is directed from north to south. And here is a copper plate. It is hanging with this pivot. Now it can oscillate freely. Suppose first we remove these two magnets and we oscillate it about the mean position, forward, backward. The oscillation of the plate will be light damped. So if this is the displacement, this is the time, then this will be the graph. Amplitude is gradually decreasing due to the resistive forces, air resistance, friction. So this is the light damping. But when the magnet is placed, now the field is directed from north to south. Now the oscillation of this copper plate is inside the magnetic field. Then the graph for the oscillation will be like this. The damping will increase. Now the reason is the plate is of the copper. It's not attracted by the magnet, but due to oscillation inside the magnetic field, varying magnetic flux is cut by the oscillating plate. According to Faraday's law, EMF is induced in the in the plate. Now the plate is of copper, which has very high number density of the electron. Number of electron per unit volume is too large. So small EMF will induce large current due to small number of the density of the electrons. So this induced current is large in magnitude. So the magnetic field induced due to the current, due to induced current, will be large enough, because when current is induced, according to right-hand grip rule, we can determine the direction of the magnetic field, right? So the induced current has large magnetic field. Due to oscillation, of plate, both sides of mean position, equilibrium position, alternating current, EMF is induced. But look, for the alternating current, for the alternating voltage, there is no outer loop. There is no complete circuit. If the current for one oscillation in this direction, for this is the other direction, this is the negative current. So there is no loop, no circuit. So the current positive and current negative both are placed at the same plate. So positive and negative currents are neutralized in the form of spark. And the spark is the loss of energy both in the form of heat and light. So the heating effect of this current is also too large. Hence, more loss of energy causes increased damping effect. And the name given to this current, which is induced in the plate, is eddy current. So an induced current in the conductor which has large magnetic effect and large heating effect is called eddy current. So this eddy current is induced in it.